All right. Well, I think I'm going to get started. Since the lecture is recorded anyway, so people who come in a little bit late can catch up later on. There's a new homework assignment, and I sent it last night. Oh, actually, sometime before midnight, which is rare. Usually, I send stuff out after midnight and before 2 a.m. So anyway, here's your new homework assignment. Your new homework assignment is the Mbr viewer homework assignment. I'm just going to go through this description a little bit here today, and then we'll continue to talk about the sample program that I was writing the other day, so that you can learn a few tricks. Not particularly for the homework assignment, but nonetheless a few maybe useful tricks. There's no drink in the classroom. Sorry. I understand the importance of caffeine, but yeah, unfortunately, we cannot drink that in the classroom. They actually make caffeine patches now. You guys know about nicotine patches? They make
they stole my idea?
Patches. Yeah, they make caffeine patches, and they have a atomizer for caffeine too. I'm not sure whether it's on the market or not, but months ago I read about this. It's a product to be released. You guys know how they have these smokeless cigarettes? And it's basically the same concept. They have these little cartridges that you can put into the device, and you just inhale, and then it gives you a shot of caffeine.
50 people out it was chocolate flavored and it also had caffeine.
Yeah, I think this one, they tout it as like really fast to absorb because it's all atomized, and it's actually your lung absorbing it and not your digestive system absorbing the caffeine.
That was one of my high-risk get-rich quick schemes. I can't believe they stole it.
We've actually now got we finally figured out how to make the suckers from like jellyfish into form patches, so they can give you medicine now that way too, on just a patch that you just slap it on, and the jellyfish stingers, they use that same kind of technology.
Wow.
And so now just kind of see.
And on the label it says no actual jellyfish is harmed in the process, right?
Yes.
We're not cutting off those little stingers from jellyfish. All right. So here's a homework assignment. It's a new homework assignment. You write a code to break a master boot record into small components, and then you check stuff, and then you print out certain information that you collect from the partition table. Okay. So nothing new. We have been talking about the Mbr, and also the partition table, and also partition records for some time now. So this is nothing new, and I will continue to write the sample program today, and that should give you a pretty good clue as to how to go about doing this homework assignment. Write the program in a source file named mbrviewer.c and use a subdirectory called mbrviewer in cisp453. So it's a good idea to put all your projects into one single folder for each class of your user home directory. So not the user, but the user of your last name. That's what I meant by that. When you are done, create a tar file using the same technique as other homework assignments, and I even repeat the command down here. So you have to just copy and paste this into a putty, or if you're in a Linux environment, I think copy and paste just works. Two things that are quite important here. The C here is a uppercase C, and these are not single quotes, these are backticks, which is basically the key next to 1 on the main keyboard, not on the numpad. Okay, so we'll go back and continue with the rest here. Input and output. You may assume the input is redirected from the command line. Your program must check to make sure that you can read at least 512 bytes from standard in, as the Mbr is exactly 512 bytes. In other words, I'm designing this program so that you can redirect from /dev/sda, and it will actually interpret an actual hard drive's partition table. Okay. But since we're only reading the file, it should not cause any harm to any actual drive. So
if you do that, you can't modify the real Mbr, can you?
If you
Redirection.
open the file for writing and then you use the write function, then yes, you can actually damage the MBR of a real hard drive.
But if you're doing the command line reading or redirect,
If you're doing redirect, then it's only serving as the input. There's no way you can change anything or damage anything in that case. You may still do not have the permission to do it unless you're root or specifically give yourself the permission to do it. Because being able to read a hard drive, as one single block device is a big security risk. Yep.
you recorded last week's session, right?
I believe so.
What's the name of that on YouTube or on Moodle?
On YouTube, you just look for my channel. Well, I'm already on my own channel, so.
I couldn't find it. I searched by the date and also by cisp453.
Did you find it?
I did not.
Okay, so you go to my channel, and then look under my video. Well, since I'm already on my own channel, maybe it won't work the same way here. Let me log out first. There we go. So just look for some profs, and then go to the channel, and then go to videos. Okay, click there, and then go to videos. It will list the video content in a reverse order. So if you look at the dates, they're kind of like backwards. This is the last class. So it's 2012-0201 ARC cisp453.
Okay.
Okay. So the quickest way is just to subscribe to my channel. So this way, whenever there's an update, you get a notification at the end of the day, and then you can just kind of save one or two of those email messages. Then you know exactly where to get back to my video clips.
And you posted that when? Was it Friday?
3 days ago.
Yeah, Friday, Saturday.
Yeah, so it was
Okay.
Friday or something.
Because I guess I was searching Wednesday night and Thursday night.
Yeah. All right. Any other questions? Okay. All right, so this is redirected from the input file. That means you don't need to use the open call or the close call because the input file is always there, standard in is always there. The output is also going to be sent to standard out, which means you don't have to open the file for output either. The only thing you want to be sure is to follow the format as specified below, as the automated grader will try to match exactly what your program generates with the expected answer. And here's a little bit of reference material. You can go to Wikipedia and go to the Mbr or master boot record page, or if you don't trust what is there because someone may be sabotaging wiki or has a blackout or something, here's a PDF version of what it looked like in 2010. But it will still work. I'm just clicking it. You basically get exactly the same content, except it is a PDF. It is static. I just took a snapshot of the page at that time. So this way we can always refer to it. You don't have to go online to read the content. So are there any questions about this part of the homework assignment? Where to find the reference material? Since the program will be compiled as a C program and not C++, you probably want to learn how to use printf to print formatted strings. I'll go through a few options with printf today. You can use man printf to get some help from the man pages, or you can Google, just say printf hexadecimal numbers, and I would think you'll find numerous tutorials to teach you how to do that. As a suggestion, you can write an MBR generator program to generate MBRs of various types to test your MBR viewer program. In other words, you can intentionally generate an MBR with specific information to see if your own program can read it back. This way you can generate intentionally malformed MBR and see if your program reports problem as it should. Such a program is relatively easy to write. You just initialize a character array of 512 bytes and then give certain things to certain locations and check whether you get the error messages. Hexdump can be useful. I illustrated how to use Hexdump last class. So if you want to use Hexdump, feel free to use Hexdump for that purpose. Yep.
So what's the advantage of using printf in this situation instead of just the write that we've been working with?
With this program, you need to use printf. It makes your job a whole lot easier because you don't have to do your own, hexadecimal printing subroutine. If you want to do that, that's fine too.
Okay.
Yep. You will find bitwise operators quite useful. The ampersand is bitwise and, vertical bar is bitwise or, shift, there are two shift operations. One is left shift and one is right shift. Depending on your implementation, you may also find type casting useful. You can cast a character pointer into an integer pointer, typo here, and then dereference it to get a 32-bit integer value. So I'll show you some of those tricks today. Behavior of a program, it should do the following. Read 512 bytes from standard in. There is a way to do it so that you don't have to read all 5 bytes at the same time, but it's much easier this way, so I would recommend this method for this homework assignment. Just read all 512 bytes with one single read operation, and then just work with the character array from that point. If your read operation cannot read up to 512 bytes, you have to print an error message and say MBR too small on a single line with a line feed character at the end of that, and then do not proceed any further, because if your MBR is less than 512 bytes, there's not enough information to process. You can ignore the first 440 bytes, which is basically the code area of your MBR. If anyone is curious about the first 440 bytes, you can use object dump to take a look at those 440 bytes. Next, you have to check, yes?
Is it acceptable if it's too large, if we get more than 512?
Yes.
Should we dump it as well, or should we process it?
You just process the first 512 bytes, because the MBR is just the first 512 bytes. Okay. Check the MBR signature. Okay, so you want to refer to the Wikipedia documentation and check where the signature is supposed to go. If the signature is correct, and then you print MBR signature confirmed on a single line with a line feed character after that. If it is not what you expect or what should be expected, you have to print invalid MBR signature 0x MNOP. That means you have to print 0x as a prefix, lowercase, and then followed by 4 hexadecimal digits, also in lowercase. MNOP, each one represents an actual hexadecimal number, so it has to be you have to make sure that you have leading zeros, for that particular value. We'll talk about that in the class.
What's the line feed character?
\n when you use double quotes. MNOP is the value of the signature byte in a zero-filled 4-digit hexadecimal number. So I just repeated myself here. After printing the message, do not proceed any further, because if the signature bytes are incorrect, that means the MBR is probably corrupted, and so there's no point in processing any further. Any questions so far? Nope. Okay. For each partition record of the partition table, and how many are there?
4.
There are 4 of them. Print the partition number as partition number X. So partition number, this part here has to be there, and then the X is the part that will change from 0 to 3. Print whether the partition is bootable. This partition is bootable, or this partition is not bootable, on a single line followed by a line feed character. You should also check for error conditions. In other words, if it is not 00 or 80 in hexadecimal, then you have to say print 0xAB, AB being hexadecimal digits that you have to actually put in, depending on what you're reading, is an invalid value for bootable status on a single line, in which case AB is the zero-filled 2-digit hexadecimal representation of the status byte. Print the first block of CHS, cylinder head sector, and you have to print it using this format here. And in this case, this is what I should see with a line feed character at the end of the line. And also X, Y, and Z are basically numbers, and they are decimal numbers this time. They're not hexadecimal, they're just plain decimal numbers. Print the last block, same thing. Print the first sector LBA address, and it is a 32-bit number. So I just want you to print it as an 8-digit hexadecimal number. It has to be zero-filled. Any questions about that? Does everybody understand what I mean when I say zero-filled? It means it has to use exactly 8 spaces. If the number itself can be represented with fewer digits, you have to use leading zeros.
Right.
Okay. Print the number of blocks as length equals pretty much the same thing. And once again, we have an 8-digit zero-filled hexadecimal number. Yes?
Oh, I was just commenting that you can't use G and H in hexadecimal, right?
You cannot, I cannot use what? GH.
Well, he does MNOP.
Yeah, well, that's why I used MNOP up there, but then I got lazy and used, start with the beginning part of the alphabet. How to turn it in, basically the same thing as you did last time. You just go to the folder where your source file is located, run this command, and then the tar file will be created in your home directory, and then you just upload it and you're done. All right, yep.
So the tools that Printf have for dealing with hexadecimals, do they do leading zeros, or is that something you have to do?
You can optionally do leading zeros. All right.
Use a dot, right?
Nope, not a dot.
Oh.
You just say, you say %0. That means,
Oh,
you
yeah, I
want to use
remember now.
leading zeros, and then the next digit specifies how many places you want, and then you use X, D, U, and a few other ones to specify the format that you want to print the number for. So what I'll do is I'm going to say man printf. Just take a look at the printf statement here, and it kind of tells you a little bit. Oh, I guess not. See also printf3. So that means you have to say man3 printf to go to chapter 3's printf topic. I think that one's going to be much longer. Oh yeah. All right. So format of the format string. It's you really have to kind of read it here, and this is not light reading. The format string is composed of 0 or more directives, ordinary characters, not %, which are copied unchanged to the output stream, and conversion specification, each of which results in fetching 0 or more subsequent arguments. Each conversion specifier is introduced by the character %, so you have to start with a % whenever you want to print a particular value, like a number, and ends with a conversion specifier. In between, so you have your beginning, which is a % symbol, you have the end, which is the conversion specifier. In between, you can specify in this particular order 0 or more flags, an optional minimum field width, which is what we want here, because when I say I need exactly 8 digits, that's your field width. Okay? An optional precision, which does not apply in our case because the precision is only applies to floating point numbers. The argument must correspond properly with the conversion specifier. Blah 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 blah. Okay, so I'll give you a few examples here. Some of these are kind of obscure. This one particularly is really obscure. We don't do anything quite that nasty. What this one is doing is to say the width of the number is also specified by one of the parameters. Okay. All right. So you guys know where to find the additional information about this. Yep.
Have they come up with a new specification newer than C99?
I think this is already C99 compliant.
But is there something newer now?
I do not know. I just use really standard, old-fashioned, printf formats. So, all right. So let's go ahead and go to where we left off last time, and then continue with our program. Are there any questions about the homework assignment? The nature of the homework assignment, what it is supposed to do? Nope. Okay. So we'll do a copy from our last class. It's 0201. And which one is our program? Read Mbr.
I do have a question.
Mm-hmm.
When you're grading our programs, will you be running it with super user permissions?
No. It would just be running inside its own little virtual machine. With regular user permission, yes. All right, so here we have our program called readmbr.c, which obviously is going to be a little bit relevant to your current homework assignment, but it's not exactly the same. All right. So last time we finished this much, and syntax on. You can't really see the colors anyway, but I can, so it makes my job easier. Okay, so last time we got up to this point, where the else is located, or let me move the cursor to that line, and I'll turn on line numbers 2. All right. So we were at line 30, which is basically saying we're ready to process what we have just read. Everything else that we did last Wednesday was about checking and make sure that whatever we read is valid at least up to that point. Now obviously I'm not going to do your homework assignment and check the signature bytes and stuff like that. So I'll just go ahead and pick some random bytes from the master boot record and use that as an example to illustrate various ways to use printf. Okay, where is it? Okay. All right. So here we have, okay, let me just magnify this a little bit, because only a small portion of this is what I need to look at right now. Okay, so this is the first part that I'm looking at, and what I'll do is I'm just going to look at byte location 444 in decimal and see what I should be seeing. It says right here usually nulls, so it should be a 4-digit hexadecimal number, and they're all zeros. Can someone tell me what do I mean when I say hexadecimal?
Base 16.
Base 16, very good. And how many bits do you think each hexadecimal digit represents?
4.
4, because 2 to the power of 4 is 16. So one hexadecimal digit is representing exactly 4 bits. How many bits is in a byte? Or in a byte? 8 bits. So how many hexadecimal digits do I need to represent a byte? 2 bytes. And here we have something that has a length of 2, and therefore we have exactly 4 hexadecimal digits to represent it. Does it make sense? This is why hexadecimal numbers are so useful. It is actually better than octal numbers, because octal numbers, each octal number represents exactly 3 bits. Unfortunately, 2 8-bit or 3 3-bit digits comes up to 9 bits, which is not exactly across a byte boundary. But 2 hexadecimal digits is exactly at the byte boundary. And that's why we use hexadecimal numbers a lot of times, because it is a very, very natural way to represent the bit pattern of byte locations, 16-bit locations, 32-bit locations, and so on. So we'll go ahead and take a look at this and see if I can do this, print out the content at this location with one single printf instruction once we have read the content into the buffer. Okay, and by doing so, I'm going to give you, I'll do that first. So I say printf location 44, what was it again? 444 as the following pattern. Okay, the first 0x has to be here because I expect your 0x, the prefix, to be as a part of your output. So this 0x is a part of the literal string. It is not a part of the format of the number that you're printing. If I want to print it out as a as a number, now %x by itself specifies I want to print the value out as a hexadecimal number. But it doesn't specify any formatting, which means if the value turns out to be 0, it will just print 0 in this case. So let's go ahead and do this the way it is specified here. And okay, next I want to specify those 2 bytes that I'm printing here. How am I going to do this? I have an array that is a buffer, buffer up here. Let me just point out here. This is my array that is storing the MBR right now. It is a buffer of, it's a character array, which means each location or each item in the array is only 8-bit long. So when I use this construct, when I say %x, it is expecting, printf is expecting a 32-bit integer. Okay? But if I do something like this, then it's not going to do it right. Okay, so I can say buffer, open bracket, 444, which seems to be the easiest way to do it. Okay, but it's not the right way to do it. Why is this not the right way to do it?
This is given.
Because you need 2 bytes.
Because it needs Well, there are several problems here. Okay, let's see if the compiler actually complains anything about it. GCC-1 wall-o. Oh, we'll just go ahead and compile to the object file and see whether we have any problems doing this. Warnings and warnings and warnings. Okay, we have two problems on line 14. At column 13, it says character constant too long for its type, enabled by default, and then on cursor location 3, or the third character on the line, passing argument 1 of open mixed pointer from integer without a cast, enabled by default. All right, so we'll go back to line 14 and figure out what is on line 14, which is actually before this part. This is our line 14, and it's complaining about this why. Can anyone remember what is the single quote and what is the double quote in C and C++?
Double quote represents a string. Single quotes represent characters.
Exactly. So I'm passing in characters instead of a string. So I have to change this part first, like that. And then I go back and recompile. This time it doesn't give me any warnings. Now sometimes C can do some typecasting without you knowing it. And this, it may or may not be doing typecasting here. I don't know for sure. Okay? So the question is, how do I know whether it is doing typecasting for sure or not?
Output the value.
Well, we need to pick a particular value that will make a difference. Okay? Does anyone understand why we need some kind of typecasting here? Yep.
Well, by default, it's going to be looking for a 32-bit length
Yes.
at the point that you're specifying.
Correct. And
Which
this is
is
specifying,
reading 2 bytes too many.
well, this is only specifying
1 byte.
1 byte.
Well, right.
The format is specifying 4 bytes. Okay? So the potential problem is, we might have a byte here that has the most significant bit turned on, which represents a negative value. And this will just print out that one single byte, but cast it as a negative value. Okay? So the question now is, how do we test whether this is doing it correctly or not? Now, I can just put in some code here. Now, whenever I put in some code only for testing purposes, I will have to write a little note to remind myself. Okay, TA, the following code is just for testing. Okay, you can do other tricks, so that this code never gets generated when you're done debugging a program. But I'll just write a note here to remind myself. Okay, so I'll just go ahead and change this one to -1. Okay. What is going to happen when I have an assignment statement like this? First of all, do you think the compiler will complain? The compiler won't complain because of what? I mean, on the left-hand side we have a char, and then on the right-hand side we have an int. Shouldn't the compiler complain something about it and say, an int is 32-bit and it won't fit in the char?
Well, you get no, because they get upgraded, right?
They get promoted, you mean?
Yeah, promoted.
Actually, in this case, it's a downward. It's a demotion because you're converting from a 32-bit integer down to a 8-bit integer. But since this is a constant, it does not complain, because if it is a constant, it already knows that -1 can be represented by a signed char. Okay, so we'll go ahead and compile the program. Definitely not a problem. And obviously, whatever the program is doing right now doesn't really, oh, okay, I forgot to link it. So I'm just I'll be lazy and not do the linking this way. That is odd. Don't you guys think it is kind of odd that it prints out 0xFFFF instead of just FF? Because I changed only one location. Somebody's going to say, attack, maybe the other 3 locations were FFs to begin with. Well, let's make sure it is. It's not. Okay, so in addition to this, I'm going to do something like that. The best way to learn is really to do some simple experiments like this kind. All right. So now, from the memory perspective, the first byte is FF, they're all ones. The second byte is all zeros. The third byte is all zeros, and the fourth byte is all zeros. Okay, so there's no way, or it should not do the, it should not print 0xFFFFFFF. It might put the FF at the beginning, it might put the FF at the end. I know which end it's going to put it, but it should not print out all Fs, right? So it seems, right? Yep.
Is it trying to represent the same decimal value in a 32-bit integer?
It is actually doing automatic cast here. Printf is doing, when we do the call printf, it's actually doing automatic cast. Let me, which one is that? This one. It's actually doing automatic cast. In other words, it is as if you have written this intentionally. Okay, the compiler is putting the typecast into a 32-bit integer automatically. Guess why? Because the compiler is being smart. The compiler sees something like this and say, oh, the format strings is expecting a 32-bit integer. And then later on, you specify something like this, and then the compiler says, that's not 32-bit. I'll help you. I'll convert it to a 32-bit integer so that these two will match. And they won't even say anything about it. It's just automatic. Okay? But don't you think we have a little bit of a problem here now? Because I'm supposed to print out 2 bytes and not 32 bits. Okay?
Yeah.
All right. Let's go ahead and change these 2 locations to some unique values, such as 0xAB for the least significant byte and 0xCD for the most significant byte. I'll keep the other 2 as 0 and 0. Okay? And we'll go ahead and get rid of the explicit typecast. What do you think the program is going to print this time? That's hexadecimal. I mean, so we don't have to do any base conversion here.
Well, it's not, they're not constants anymore, or yeah, they are.
Yeah.
But aren't all hexes integers anyway?
Hmm?
In C, isn't hex an integer?
They're integers. But the question is, what do you think printf is going to print?
Whatever the integer value AB comes out to be, isn't it?
Well, it's still in hexadecimal, so AB is still AB. There's no need to convert it to base 10 or any other bases. So AB would definitely be a part of the output. The question is there anything else in the output?
Why wouldn't it? Oh, you're %xing, I'm sorry.
Yeah,
Okay,
I'm using %x already.
Okay,
Yeah, so there's no base conversion involved here. So we know AB is going to be there because AB is the byte that I put into location 444 in the array. The question is, what is it going to print? Do you think, okay, there are a few options here, right? Do you think it's going to print ABCD? Do you think it's going to print CDAB? Or do you think it's going to print AB by itself? Or do you think it's going to print FFFFFAB?
What is A in binary?
A in binary is 1010.
Okay, so then it's gonna think it's signed again, right? And so we're gonna get all EDFs. I think.
Exactly. It's going to print FFFFFFAB because AB, the A in the AB specifies the most significant bit of that byte is on, which means in the signed interpretation, that's specifying a negative value. I don't really care which negative value, it is negative. So when you cast a negative value that is originally represented as an 8-bit number to 32-bit, it does what we call sign extension. In other words, it will just fill up the other 3 bytes with all ones. So that the 32-bit representation will be representing exactly the same value as the 8-bit signed number. Yep.
What if you made buffer unsigned caret?
If you make it unsigned, then it will just print AB because it will still do the sign extension, except in this case the sign is always 0. Okay? So, but let me just confirm this first. Okay, let me just confirm the behavior of this program. And sure enough. All right. Well, someone is going to say, "Oh, attack, that's you being silly because Why do we want this buffer to be signed? We'll just change to unsigned, and that should fix all the problems. Well, it's not going to fix the problem because the nature of the problem is not that. Because in this case, it only prints AB instead of BCAD. No, CDAB. Sorry. Okay. So we still have a problem here. What do you think we have to do to fix this particular problem? Well, there are several ways to do it.
I would bit shift the more significant of the two over by 8, and then
Okay.
cast that to an integer and add it to the other one cast to an integer.
All right. That will work. Okay, so the first suggestion is to do it like this. Okay, this is the least significant byte, which is fine by itself already. Okay, we don't have a problem with that. However, we also want to do something like this: buffer 445 and bracket. This is supposed to be the more significant byte, so we have to do a bit shift by 8 bits to the left-hand side. So when you bitwise OR these two, one will specify the least significant 8 bits. The other one will specify the most significant 8 bits, and then it will print out the number as a 16-bit number. Yep.
I'm not sure, but isn't that going to shift by 8 bits before doing the typecast, and therefore shift 8 bits in an 8-bit space and just lose all the data or do nothing?
You may be right. I'm not sure. I'm not sure whether it will do the conversion. Well, let's go ahead and run it and find out. I know what your point is, but it actually does it correctly. I think it does the base conversion already. I mean, it does the extension when it sees something like this. So it's already automatically casting that to an integer before that.
And would 445 really be the more significant? I thought it would be the less significant.
It is the more significant because it is the little endian notation.
Okay.
Okay, so that's the other part that you guys have to deal with. Okay, how many people already know what is the endianness of a number? Little endian versus big endian. All right. Well, people who took CISP 310 from me should know. Because we spent quite a bit of time talking about little endian and how it is very, very important. All right, so let's go ahead and take a look at the significance of endianness, or why is it important to understand whether a number is little endian or big endian. Let's pick one of these items here that you have to print out anyway. Let's take a look at this one. Okay, number of blocks in the partition in little endian format. So in this case, it is very explicit that this number, as a 4-byte number, is a little endian number. Okay, before we go any further, let me just ask you this question. Do you think a 32-bit number can represent, let's say, 257? That in decimal. I give you a 32-bit integer, and I ask you, can it represent the value 257? I mean, signed or unsigned, it doesn't matter, right? I mean, signed, a 32-bit integer can represent about 2 billion to positive 2 billion. Unsigned, it can go from 0 to 4 billion. And 257 is well within that range, right? Okay, not a problem. Next question. How am I going to store 257 as a 32-bit integer? That's a different question. Well, attack, that's so easy, right? I mean, this is trivial. It's okay. We'll take a look at 257. 257 as a base 10 number. In base 2, it's quite easy. It's 1 0 0 0 0 and 0 0 0 1. Let's see. That's 1. That's 1, 2, 4. I think that's right. Okay. We'll call it right. Okay. Now you can definitely see the binary representation doesn't really need close to 32 bits, right? So how do I write it as a 32-bit number using leading zeros? How many zeros do I have to pad on the left-hand side? This is 9, you need 32. 32 minus 9 is 23, okay? So we'll just have to write 33 zeros. That's 24, 23 more, and then we have, all right, there we go. Here's our 32-bit, number.
It's 4 bits. Yeah, it's 4 bits too long. 4 zeros too long.
Is it 4 bits too long? Oh. Okay, there we go. I cannot count. All right, but here we have a 32-bit integer. So no problem. I know exactly how to represent 257, a base 10 number, as a 32-bit number. The next question is, how do you store that thing in memory? You can be storing that in memory as a char array. You can be storing that in your partition table as a 32-bit number. That's the question. Because the memory of your 386 architecture is byte addressable. The sector, inside the sector, the 512 bytes, is also byte addressable. In other words, every time you store something, the smallest item, the smallest quantum you can store is a byte. And here we have 4 bytes, right? Here's 1 byte, here's another byte, here's another byte, and here's another byte. So the question is, which bytes gets stored first? In other words, which byte has the lowest address? That's the question. There's no right or wrong, okay? There's no such thing as, oh, I think the least significant byte should be stored first, or I think the most significant byte should be stored first. The only thing that will be kind of like questionable is to store the middle 2 first, But as long as the processor or you do it consistently, that's not wrong either. So the only thing that is in play here is, what is the standard? What is the processor doing? What is the Mbr specifying? That is the question. When we get back to this documentation here, it is very clear that the Mbr is specifying little endian. Little endian means one thing. The least significant byte is stored first. It has the lowest address. Are we doing okay so far with that? So that means when you switch back to this view here, this byte is stored first. Then it will store this byte, and then it will store this byte. This is the last byte. In other words, this byte, the byte that I'm highlighting, has the highest address when you store it in memory, and it is the last byte when you see it in the Mbr. Are we doing okay so far? The little endian versus big endian standards. We're doing okay? And that's why in my program, when I interpret those 2 byte locations as if it is a 16-bit integer, this is the way I do it. Because this is the low byte. It is at location 444. It is considered as the least significant byte of the 2. Location 445 stores the more significant byte, and I need a left shift operation so that it becomes the more significant 8-bit of the integer. Are we doing okay so far with this? Yep.
If we were trying to represent a hexadecimal value, like we have to do for one part of the assignment, the signature, would we end up reversing it when we printed it out, or would we still just print out, first byte, second byte? And that's
You just print out first and second byte.
And we do the opposite here.
Let me. Oh, the signature, I think you have to print it as if it is a 16-bit number. So print it out as if it is a single 16-bit number. That's a good question. Does everybody understand why there's an ambiguity? No? It's because when I specified the homework assignment, I did not make it very clear. Okay, let's go back to that portion. Okay, right here. I guess it's kind of implied, because I said, invalid Mbr signature and MNOP on a single line, it is the value of the signature bytes in a zero field 4-digit hexadecimal number. So I should probably say this, and use little endian interpretation for that purpose too. Okay, so you're basically treating that as a 16-bit number. I think I have just done your homework assignment.
Sorry.
That's okay. I mean, there's still enough of this homework assignment to make it, a good exercise. All right. Any question here?
You're recording this, right?
Hmm?
You're recording
I am recording this. Let me do another part of your homework assignment. Yes.
Can you explain a little bit more about the OR and the AND operators?
The OR operator is just the bitwise OR operator. When we specify OR and AND in logic, in logic it's either true, false. The two values are true, false. But you can kind of look at true as 1, and you can look at false as 0. So when you look at true, false as the numerical values 0s and 1s, then it starts to make sense to have bitwise operators. Let me just kind of quickly go through the bitwise operators here, because that's also something that is very, very important in this class. Okay. 0 or 0 is 0, bitwise OR. Okay, it makes sense because false or false is false in logic. 1 or 0 is 1 because true or false is true. Okay, so you guys should know this part already. I mean, this is relatively.
Wait, hold on. So this is This is a
not exclusive OR. It is just OR.
Okay.
Just a regular OR. And then we can do the similar thing with AND. Okay. This is bitwise AND, not logical AND. Okay. That part we know. False or false. False and false is false. True and false is false. False and true is false. True and true is true. Okay? That's a typical truth table for logic. Except most of the time, you guys have used double OR, which means logical OR, and you use doubles ampersand, which means logical AND. Okay? But this is correct. When you use double OR and doubles AND, this is actually incorrect. Because the C standards, okay, let me just give you this one here. True or logical or true is what?
True.
True, but as a number, what should I put here?
1.
It's a trick question. This is a very, very tricky question. When you read the NCC standard, it says it is just anything other than 0.
Right.
That is the difference, okay? So all you can say is this is non-zero.
So that's probably an implementation defined then.
It's whatever the compiler implementation wants to do, okay? But anything other than 0 is true. But when you have bitwise operation, that's not the case.
It's 1 or 0.
It is always 1 or 0 for that particular bit position. All right? All right, so now let me ask you another question. In C, what is that? It's
Non-zero.
3. Exactly, it is non-zero. Because this is non-zero. 0x3 is non-zero, which in logic means true. 0x8 is non-zero, which in logic it means true. So we have true or true, true, logical or true, which is true. And true just is represented as non-zero. We don't know what is the value that your compiler will use to represent the result. It may pick just 3, it may pick just 8. It may give you 1, it may give you FF, it may give you FFFFFFFFF.
Could it
We don't
even
know,
give you
and we don't care,
Could it
right?
even give you a negative number?
Yeah,
No.
but negative is not 0, okay? However, if you convert this to logical OR, then what is it going to give you?
1.
Decimal.
It will give you non-zero for sure, but you know exactly the value it's going to give you in this case. Well, let's go ahead and convert the numbers to 4-bit numbers. What is hexadecimal 3 as a 4-bit bit pattern?
Yeah.
Okay, and then we have an OR operation here, bitwise OR. And what is 8?
1, 0, 0, 0.
In base 2. And then you perform the OR operation for every position so for every column,
1, 0,
you
1,
just
1.
do it. Yeah, exactly. 1 or 0 is 1,
11.
or this is 1, 0, 1. That's a bitwise OR operation. Okay. Are there any questions about bitwise OR?
So it's a little bit like doing complementing.
No, it is performing the same thing as a logical OR, except it's applying that to every bit position. Because if you think about, you're doing it to every bit location, you can still say, 1 or 1 is non-zero. But if you only have one bit to represent a value, what is non-zero?
1.
Has to be a 1, right? So you can kind of look at it that way. Okay. Okay, let's take a look.
How do you represent exclusive OR?
Exclusive OR?
Yeah.
It's the caret symbol. Yep, the caret symbol means exclusive OR, which we don't usually use in this class for our homework assignment. Exclusive OR is very useful. It's useful for many, many things. It's just that we don't have any use for this homework assignment yet.
What is it used for other than encryption? I've never figured that out.
Exclusive OR?
Yeah.
You can use it to swap bytes, and there are there's a lot of trick you can do with exclusive OR. Yeah. You can turn things on and off. You can toggle bits. In embedded system programming, the bitwise OR operator is very useful because if you have, because we have registers, I/O registers, input/output registers, and each bit in an input/output register can control a single LED, whether the LED is lit or not. Okay, so if you want to blink one LED without changing all the other ones, you can bitwise exclusive OR that with the LED that you want to blink. Then the other LEDs won't get affected because 1 exclusive OR with 1 is still 1, 0 exclusive OR with 0 is still 0. So those bits or those LEDs will not be affected. But 1 exclusive OR 1 is 0, you turn something off. 0 exclusive OR 1 is 1, so you turn something off into something that's on. So you just flip the state of that bit.
Okay.
Yeah. Embedded system programming is very, very fun. It's very different from regular C programming.
You don't have all your libraries in embedded either, so you'd have to implement like a quick sort or a double sort or something.
Well, it's just the lack of convenience. Okay, what about something like this? Bitwise AND. I don't think this is going to be very challenging.
0.
That's a 0.
1. 0, 0.
That's right. Okay. So bitwise AND is for masking out bits. Bitwise OR is introducing additional bits of 1. Okay. All right. So are there any questions at this point about bitwise OR and bitwise AND operations? No. Okay.
So when you're doing that, when you're printing that up, it's basically constructing a string or
formatting the output.
an output.
You mean if you look at my C code? You mean this part here?
Yeah.
Yeah.
It's
This,
adding those together.
yeah. Only this in the format string is specifying I want to print an integer, 32-bit integer in hexadecimal. That's all it's saying. This is the argument to supply to the format, and basically say this is the value that I want to print as a 32-bit number, but I want it to be printed in base 16. Is that okay?
Oh, it's telling you to print it in base 16?
Yep. The X means base 16. If you put a D there, it is signed decimal. If you put a U there, it is signed unsigned decimal. And then if you, there are other ways other things you can specify.
So why was it printing all the F's before?
Huh?
It was printing all the F's before because it was negative? Or
The
was it
extra F's are printed because of sign extension.
because of the sign?
Because of sign extension. Now it doesn't do a sign extension because I changed my buffer from a char array into an unsigned char array. And because it is unsigned, that means the sign is always 0. So sign extension just pads zeros.
Okay.
All right. Any questions?
So
No.
the-
Yep.
Go ahead.
All right, so the order that statement gets read in, does the bitwise shift happen before the OR?
Yes.
That is correct, because it's inside its own pair of parentheses.
Okay, so when that 445 gets put in, it's just being put into all the zeros. So
Yeah, 445 is this part, but since the whole thing is in parentheses, so it is shifted 8 bits to the left-hand side before it is ORed with buffer at 444. Okay.
What happens to a shift just shifts the numbers over. What happens to the numbers that aren't?
That is overwriting.
Yeah.
It shifts it out of the number.
So they no longer exist?
That is correct.
Okay.
Well, the most significant 8 bits would be shifted out, but everything else just moves by 1 position. Yep.
I just want to make sure, this is shifting a temporary member of the addition, right? It's not shifting the actual array that we have.
That is correct. We are not changing an element in the array. We are referring to an element in the array and then use that value and then shift that value before we use it again for the bitwise OR operation.
Okay.
Yep.
Would it be appropriate to review for me just for a second the signed versus unsigned? Where's that sign represented in the byte? Or is
The
that just,
sign is
my
represented by the most significant bit of a number.
Okay.
Because when you represent a negative value in binary, it is represented by 2's complement. It's one way to represent negative values. It turns out to be a very convenient way to represent numbers. But in that representation, all negative numbers will start with a 1 as the most significant bit. If you look at a 16-bit signed integer,
Right.
then bit 15 is the one that is the signed bit.
Okay.
Because we count from 0, so that's why when
Got
you
it.
have 16 bits, it's bit 15 being
Okay.
the most significant bit.
Okay. Thank you.
Okay, now I have just introduced another problem here to help you do the homework assignment. I have just changed the most significant hexadecimal to a 0 here. Okay, so we'll go ahead and run this program again and then see what kind of problem we are going to run into this time. Dab instead of 0 dab, right? Because I want your program to print a certain number of digits. In this case, it's flexible. Okay, if I only have to use 3 digits, it prints only 3 digits. Okay, so the question is, how do I force it to use exactly 4 digits or 5 digits or 6 digits or 8 digits?
Percent 4x.
%04. Yep. So basically, what you can do here is you can specify 0, which means leading zeros, and a 4 here, which means I want it to use exactly 4 characters to print out this number, or at least 4, I should
Yeah.
say.
Should the percent be first?
Oh, you're right. No wonder it's not syntax highlighting. There we go. %04, and then the x. Okay, so we'll save this.
So it's 0 and 4 because you're telling it use 4 spaces and use
Correct.
leading zeros?
Yep. The 0 is for leading zeros, and then the 4
Field
is
length.
for the number of positions.
Okay.
That's actually the least number of positions. If you have a number that requires 6 digits, it will use 6 digits in this case.
Okay.
Any questions about printf? Yep.
If you made it 0B instead of AB, then that wouldn't be a problem, right? It would stick the 0 in there in this case.
Correct.
So if you had, if would it print out at this point 0D, 0B for the output?
Yes. Yep.
Thank you.
All right. Very good. But I am kind of surprised that nobody says, but Tack, I don't want to learn printf. It's so archaic. My C++ teacher tells me not to use printf. Well, if you don't want to use printf, you can do it something like this. I just want to present this because it is a simpler solution in many, many ways. So what you want to do is to know what is put s. And I just mix up the commands. Okay. Okay. Put s is put string. That's the name. That's basically what it does. All it does is it will print whatever s is pointing to, which is a character array, and it will print it to standard out. That's all it does. It doesn't do any interpretation. It doesn't know how to print hexadecimal numbers. It doesn't know what octal is. It doesn't know anything. It just says, give me a string, I'll print it out. That's all. okay? Or if you prefer, you can even not do that. You can write your own print put s function, okay? So let's do it the hard way, and by doing so, I want to show you guys, get you guys back into the C programming, routine. Yep.
Go back to the man page for a second.
The man page.
Why is it an int function? I mean, what does it return?
Well, that's what you can look for return. It returns a non-negative number on success or EOF as a constant on error. So the man pages are truly, truly helpful because it really does tell you things. Sometimes it's in a cryptic way. But
For me, it's always cryptic. For me, it's always cryptic.
Yeah, but that's live, right? All right, so we'll go ahead and write our own function, okay? Because I don't want to use printf. I don't, I'm too lazy to print, to read printf, which has a gazillion combinations of doing things. So I don't want to deal with it. So what I'll do is I'm going to do it all by my own code. The only thing I need that I cannot do on my own is how do I send a character out to standard out. That's the only thing I cannot do by myself. Is that right? Okay, so I'll just start with that. Okay, so we'll start with that and just say, tags put s. Okay, and we'll just, give it a pointer, like that.
I thought you were doing. I thought you were converting something.
I'm printing a string out. That's all I'm doing here.
Okay.
Give me a string, I'll print it out to standard out. Or if you prefer to make it more general, you can give me a FD, a file descriptor, and I think that can be const too because I'm not changing it. All right, so how am I going to do this? How is a string represented in C?
Well, there's two types of strings. There's the string class, and then
There's no class here. This is strict C.
Yeah, it's a C string.
Strictly
They're
C.
represented as characters.
It's an array of characters. How do I know where the end is?
It's a null terminated.
It's null terminated. Very good. So, so that means I can do something like this, right? While whatever s points to is not null, do the following. What am I going to do here? Well, let's see here. Let's just say that I'm not doing any error checking, which is bad by itself, but I'm feeling a little lazy today. So I'm just going to say write. Write requires you to specify to which file handle you're writing. Well, I'm just told to write to file handle FD. I'm just going to write to that FD. Okay, it may not be the wrong, maybe the wrong file descriptor, but I don't care because people told me to write to that. I'm writing a single byte. Let's see, the byte count is the last, so I have to specify what
Buffer.
I'm writing to, which is very convenient because s as a pointer is pointing to the character location that I want to print. And I will specify exactly 1 byte. I believe that's the right format.
I don't think that's going to work because in the man page it says you have to have a void pointer.
But anything can automatically cast to a void pointer.
Oh, okay. Yeah.
Oh, that's right. I have to do that. Well, let's do a post increment here. I was about to write a s equals s plus 1, but that's okay. This works too. All right. So I think that will work.
What does incrementing the pointer do?
Huh?
What does incrementing the pointer do? Could you go
So
to the
then I'll
next
be
end?
ready to print the next character and then the next character
okay.
until the pointer points to a null character. Then I'm done. Yes.
Okay.
Won't it not let you do that because you have it as a constant?
Ah, very good. You are bringing up the fact that this is a const here, and this operation may have a problem. Well, the const applies to what s points to, but not s itself. So I can change it to point somewhere else. I just cannot change what it points to.
Oh, that's clever.
Okay.
That's clever.
And as I said, I'm doing this not because I think you want to re-implement everything in the C library, but to bring you guys back up to speed in terms of C programming, concepts that you should probably know but may not have a good recollection of exactly what it means. Yep.
Are you passing it through as constants?
Yes, I'm printing out constants.
No, she's asking why.
Oh, why? Because I'm just printing out the string. Whatever I pass as string s to here, I just want to print it out to file descriptor.
Take away the constant.
I
What
can get.
difference does it make?
because I don't want to accidentally change that string.
Just for safety.
So yeah, because if you do it this way, the compiler will enforce that and say that whatever the pointer
Yeah,
points to,
that's-
you cannot change it.
Okay,
Yep. You had a question earlier.
Yeah, I was just gonna say, just to check real quick, if you put the const after there, then you wouldn't be able to
Right.
increment it, right?
Yeah.
That is correct. You can actually have it both ways.
Yeah.
You can have it like this, then the pointer itself cannot change, and you cannot change what it points to either.
Oh, that's what I was gonna ask. So you can change the pointer, what it points to, but you can't change the address if there's only one const, right?
Well, it depends on which one you have. The way it is right now is you can change the pointer, but you cannot change what it points to.
That's just
Oh,
changing your
okay.
local variable, what you're doing now though, right? It's just changing the,
You're just changing the
The
parameter,
scope.
yes. You're changing the parameter.
parameter.
Yep, but
Oh,
not
that's
changing
tricky.
what it points to. There was a hand back there.
Oh,
No?
not anymore.
Okay. All right. Well, let's check and make sure that this works. And well, let's go ahead and. Well, since the program has already progressed up to this point, I'll just go ahead and comment out my own program here. Now, if you want to comment out multiple lines, one really quick and nasty trick to do it is use that conditional compilation.
What?
It's conditional compilation. So that means everything within #if0 and #endif will not get compiled.
It's faster to do the block comments. It's faster to do the block comments.
Well,
This
the
is easy to find.
block comments has a problem because if you have comments inside that, comments cannot nest.
Oh.
At least it's not in the standard C. I think some compilers can do that, but it's not in standard C. This will nest too. Yes.
why is it if 0, wouldn't it be if 1? Or
No, if you have #if1, that means you want to include whatever is between the #if and the #endif. #if0 means because
Oh,
0
okay.
and 1 are true false, right? So you're saying #if true, whatever that thing is true,
Oh, got
then
it,
you're
got it. I
including
got it.
whatever is
I
in
see.
between. So this is a fairly standard trick because you can see the VI understands it too. Do you see how VI changes the syntax highlighting? VI is really smart. It knows all the tricks of a C programmer. All right, so let's go ahead and implement the same thing here and use text put string. I'll give it the standard out FD, which is 1, and then I'll give it the string location 444 as the following bit pattern. So everything that I should print out, verbatim, I'll just supply it like this. But I cannot supply any more because the next part is the actual number. Is that okay?
Yeah, so just call it again.
No, I cannot just call it again because I have to use a base conversion thing to print it out as hexadecimal. But before I go any further, I'll test the program. You can see that I don't really, write the whole program and then just test it and go like, yeah, let's hope that it works, right? Which is also important. Okay, I'm going through the programming, routine here just so that I can show you how I would write a program. I wouldn't write any more than 5 lines or 10 lines before I run the program again, double check everything. If it's good, then I proceed. If it doesn't work, I know what 5 or 10 lines I just added. Okay, you can also add revision control to the whole thing. You just basically say, okay, this program, does everybody understand what I mean by revision control?
You mean like get?
Get, git get, CVS, RC, even RCS will work really well because we have single person projects here. You guys are not supposed to work together. I'm pretty sure someone who can set up a get server, on the internet probably does not need to work with somebody else in this class. So I'm not too worried about that. All right, so the program is working correctly. Even though the output seems to be garbled, it is actually correct. Because the output has exactly what I specified in the program. Location 444 has the following bit pattern, 0x, and then it has the prompt again. So it seems like the program is wrong, but it is actually correct because I did not specify an end of line character. And as a result, the output of the program is followed immediately by the prompt right after that. Okay, so little things like that, you really have to understand why it looks like this and whether the program is actually correct when they output something like this. Okay. All right. So far so good. What I'm missing right now is the base conversion. I want to print out a number as a hexadecimal number, and I want leading zeros. Okay. And to do that, well, there are several ways to do it. we'll say print hex, okay, for the lack of a better name. And we'll give it a file descriptor. In this case, we'll give it a integer to print. I'll just give it a regular integer in this case. Now, for those of you who want to be a little bit more careful with this sort of thing, you can give it int32_t, which means I want this parameter to be exactly 32-bit, platform independent. In other words, when you specify int32_t, GCC will interpret this argument as a 32-bit integer, whether you're compiling to an i386 processor or whether you're compiling to an 8-bit processor like the AVR, it will still make sure it has the right length or the right width. Okay, which is very important in some programs and not so important in other programs. When you do embedded system development, you will find that this is extremely important to always specify the width. Yep.
If we're going to go to that length, wouldn't it be easier just to specify a 16-bit integer?
Well, because in the rest of the program may require the printing of longer, up to 32-bit, you can always cast something to 16-bit by only specifying how many hexadecimal digits to print. Okay. So we just call this a number here. And this program, as it is, will not compile because int32_t is not a built-in C type. It is a type that you can import from, I think, intype.h. I may be wrong. I wrote some notes on that. I think it is under. Well, I guess we'll find out soon.
I read out inttype.h from a previous lecture.
Yeah, I think one of the header files already included that, so I don't have to pound include it explicitly.
So what aren't we allowed to include then?
Anything. But GCC has to compile it.
What if we make our own libraries and it won't compile on your system but it does on ours?
Well, if you're running GCC, it shouldn't
Well, you have to
matter.
give me a whole make file and your library source code in that case. All right, so now we have a subroutine that is supposed to print hex, and I probably want to make this a little more general. Otherwise, I have one subroutine to print out 4 digits and another one to print 8 digits. That's just not very smart, right? So we'll just go ahead and say const length. How many bytes, or how many hexadecimal digits am I supposed to use? Or if you want to be number of digits. Okay, that's better. Because now I can do it recursively. You guys still remember recursion?
Of course.
The subroutine calling itself? It actually makes sense in this case. You can do it iteratively, but the iterative version of this is actually longer than the recursive way. The recursive way says if num digits is greater than 0, oops, pseudocode, okay, have it from another class, then you do the following, because if num digits is less than or equal to 0, there's nothing to do. All right, if it is greater than 0, then we'll do the following. If num digits is greater than 0, that means I'm responsible to print at least 1 digit, right? Because there's at least 1 digit to print. Well, guess what? I'm lazy. I'll just print that 1 digit first. Let's see. Should I print it first, or should I pass it on to somebody first? I should pass it on to somebody else. Okay. So the first thing I have to do is to ask somebody else to print the more significant digits first. Does it make sense? Because when you look at numbers, numbers are printed from left to right. But the leftmost digit is the most significant digit.
Little endian. Little endian.
No, it has nothing to do with endianness. That's just how we write numbers. Okay? So I have to I have to tell somebody else to print the same number. Well, but not the same number, because whoever has to print the number now do not have the other 4 bits to deal with, because I'm dealing with those 4 bits. So those 4 bits are fine. That person does not have to handle that. And then it's number of digits minus 1, because there's 1 fewer digit to print for the next guy. When that guy is done printing all the more significant digits, it's my turn. So my turn is just to print 1 single digit. trying to think of an easy way to do it. Nope, there's no easier way. Okay, fine. We'll have to define one single char here. And let's just call it X. Okay. So now I have to decide, how I want to print this one digit. Okay, so I have to say X equals. I'm trying to decide whether to do it on one line or do it on 2 lines. That's why I'm thinking so hard.
Just one.
Yeah.
Just
One?
do it on one.
Always.
Because if I do it in one line, there will be some replication which I don't like. I cannot do it on one line and not to have any replication of expressions, which is what I'm trying to avoid here. So I'll do it in 2. Okay. All right. So in this case, it will be num ampersand 0f on one line, and then the next line is determining whether x is greater than or equal to 10. If so, the ASCII code of A. If not, the ASCII code of 0. And then I can write it out. Write the location, the address of x, 1 byte out. All right. Let's go back and see what I'm actually doing here. The recursion part, if you don't quite get it, don't worry about it. I'm just printing. At line 24, 25, and 26, you should understand, because even the iterative or the repetitive version should have these lines here. Okay. Line 24. What is line 24 doing? We're masking out everything except the least significant 4 bits. Okay, 0xf specifies the least significant 4 bits. Oh, what is the other way to call 4 bits?
Nibble.
A nibble. And how do we represent a nibble? It's a hexadecimal digit. Okay, so we're focusing on the 1 digit that I have to print at this point. Okay, unfortunately, I cannot just print x. Why can't I just say write ampersand x1 right away? Because I will be printing some control characters. ASCII code 0 is a control, I think it's control at. ASCII code 1 is control A, ASCII code 2 is control B, and so on. So I'll be printing some unprintable characters on the screen. That wouldn't be very helpful. So I have to convert 0 to 15 to the ASCII codes corresponding to 0 to 9 for the lower half, and then A to F for the upper 6 numbers, or the upper 6 values, right? Because that's what hexadecimal numbers are. Hexadecimal numbers go from 0 to 9, and then we borrow from the alphabet from A to F. And that's what line 25 is doing. Line 25 is saying, oh, x by itself is only from 0 to 15, which I cannot print. So I have to add the ASCII code of A in some cases, and I have to add the ASCII code of 0 in some cases. And this is actually wrong too, because the ASCII code of A, I cannot just add it, because then it will be A plus 10, the ASCII code of A plus 10. So I have to remember to minus the 10 as an offset first. So x plus ASCII code of A minus 10 is what I need to print out A, B, C, D, F for the values 10 to 15. Do you guys still remember how to use the question mark and the colon?
Yeah.
It's basically if, then, else. Okay? If the condition is true, I pick this expression. If the condition is false, I pick the second expression as the overall value of the entire expression. Okay? Are there any questions?
Yeah, I'm confused at the A-10 portion of that.
You mean this part here?
Yes, yes, yes.
It's the ASCII code of A minus the value 10.
I got it.
And that is necessary because I just want to add, I want 10, the number 10, to be printed out as lowercase a. So if x is greater than or equal to 10, I want to add this amount to x. Okay? But if x is less than 10, I just want to add the ASCII code of 0, because the value 0 should be printed out as the ASCII code of 0. The value 1 should be printed out as the ASCII code of 1. The value 10 should be printed out as the ASCII code of lowercase a.
Okay.
Okay? Because if I forgot to, as I originally did, if I do not have a -10 here, then the value 10 will be printed out as what? B, C, D, E, yeah, K. Yeah, but you will notice because it's a letter that you should not be printing out as a hexadecimal number. Okay? The recursive part, you know, you don't have to really get that part. You know, you can do it with a while loop too. I mean, you know. Okay, so we'll go ahead and test it and see when it works.
Why do you? I don't understand why you use A though. I mean, shouldn't you use the character code? Or
Quote A quote is the ASCII code of lowercase a.
okay.
So I don't have to look up the ASCII code table. Okay.
Do you need to tell it?
Well, we're running out of time, so let me just kind of quickly finish this part so that the next class can come in. Pretty sure it works, you know, but it doesn't hurt to give it a try. So this would be the same thing here. And to that. Paste. Okay, we got all the parentheses. And test it. Ah! Forgot to recompile first. Too few parameters. I forgot to specify how many digits to print. Before. Recompile, rerun. And it printed out 0x0DAB, which is exactly what it is supposed to print. Okay? So I think this will give you guys a head start on the homework assignment. I didn't do the whole thing, so there's still enough fun left in the homework assignment. It's due 1 week from today, so we have quite a bit of time to do it. All right, I'll see you guys on Wednesday.